So we're going to take the last week of the things you need to know for knowledge required by Google class. And today we're going to do something a little bit different. Instead of doing stuff on a whiteboard, I'll be typing the code into an IPython notebook. I'll try and make the font very large, so hopefully it will be readable. There might be a lot of other things that are no longer readable, but we'll do what we can. And we're going to take on what we talked about doing at the end of last class, which was to use a memoization function to improve a dynamic programming problem. And the problem we're going to be talking about is the knapsack problem, which is a really kind of basic problem. And it can be solved in different ways with different conditions. But we're going to talk about how to solve using dynamic programming, because that technique comes up in more complex problems oftentimes. And so the first thing we're going to do is we're going to use memoization to speed up the runtime for this function. And if we like, we can compare versions that are memoized versus versions that are not. We'll see if we have time to do that. But right now we're going to start with writing a function that memoizes something. And so to be a memoizer, it needs to remember what values were called before. And if those parameter values have been called before, just spit out the output without actually calculating from the function again. And so there's an easy way to do this in Python, which is using decorators. And we'll build an example of one of those. So, the first thing we want to do is we want to store values. And we want to have them associated with some key values, which are the parameters to the function that's being called. So in Python, what would you use to store key values pairs?
Dictionary.
Yep. So we're going to create a dictionary, what's called cache. And the memoize function is going to take some function as an input. And this is a function that we're going to be adding a cache to. And so if you want, you can create a cache or attach the dictionary to that actual function. And so this way, if you want, you can then modify that dictionary. You can take a look at it when you're done. You can clear the dictionary if you want at any time, and you have direct access to it. But the way that decorators work is that when the function in this case, that's what you put it up here, is getting called, it's actually going to call a kind of a function that wraps around the other one, and then is able to be accessed through that. And so we're going to create a function inside of this that's going to get called with whatever arguments are passed to it. And one of the things this is going to do at some point in time is call func with the arguments that was passed. So this is something, this notation in Python captures all of the positional arguments in a list or in a tuple. In this case, we're just passing that same list of input arguments into the function. But when do we want to call the function in this case?
Have it ever been run before?
It's never been run before. So we're going to have if arg's not in cache, run the function. What do we do when we call the function?
We store it.
Yep. And now, since we've guaranteed that everything is in the cache, if you call the function with some parameters, how do we give you the output? What do we return?
Cache args.
Yep. The stored version from the cache.
Should the two star, should those both be args?
These two?
No.
Yeah. Good point. Yes. Good catch. Thank you. And so
What's the star for again?
So the star is what makes this kind of the equivalent of a var arg in, where you have a variable number of inputs.
Oh, okay.
And so this will take all of the positional numbers and put them in a list, in a tuple, that you refer to as args.
So let's say you were writing this, and so like Python has args and like keyword args,
Yeah.
right? So would you have to write this, says you'd have to write explicitly to cache both?
Yes. And so, one thing in particular is this only captures, the single star only captures positional arguments. If you want to capture, keyword arguments as well, you have to have a separate declaration for it that relies on this structure. But it also allows you to do things where you can set it up where you only cache the values based on the arguments, and then you can use the keywords for passing around different types of parameters.
I see.
And
Wait, I don't. What? Wouldn't this mess up if you didn't define the metaphor?
yes, yeah. And so I mean, that's the thing. Like, you can do cool things. You can also do very broken things using these techniques. And so, like, if you, and so if you wanted to do a system that relied on both of these, you would have to somehow make some variable that took the args and keyword arguments and added them together in some way. This line wouldn't actually run, but you need to do something that turns them into a kind of a frozen set input. I think that works.
Could you just set the params equal to a tuple containing the args and keyword args, and then use that as a key?
Yes. It's for one of the issues is that the keyword arguments come in as a dictionary, and you can't store dictionaries as the keys to other dictionaries.
Okay.
And so that's kind of the main problem, is that the values that serve as a key for the dictionary have limitations on what they can be. So for example, they can't be lists, they can't be dynamic data structures. They have to be fixed data structures like tuples.
Okay.
And so within that kind of limitation, and so there are ways around all these problems, but for this problem we only need a memoized function that's this complex. So we'll leave it at that for now. And so when you do this whole decorating a function with this, we're going to pass that function in, and we're going to return a slightly different function, this memoizer function, that's going to take the same arguments that whatever function we care about is taking, and it'll pass those on if it needs to, otherwise it'll just return the value from the cache. And so what that'll end up looking like, or the syntax for that, is pass in declare the decorator, best, and this will take items and await. And so this will be the syntax we'll use for it. But first we want to talk about what the problem is we're actually trying to solve. So the problem is that we have some bag that has a maximum amount of weight. In this case, we'll say it's 8 units. Use pounds if we like, kilograms, or anything else. And then we have a series of items. And this series of items will store as a tuple. It will have pairs of weights and values. And so the first item has a weight of 2 and a value of 4. We'll have another item that has a weight of 5 and a value of 15. Another item that's the same as that first one. And then lastly, an item of 1 and 1. And so, can anybody think of quickly what the solution to this that we're eventually going to want to see is? Like, what 3 items would give you the most weight? Or what set of items?
Can it be,
Or the most value for the weight?
can it be any number of,
Nope, in this case we're just going to do a 0-1 problem where you can only include or not include these items. But in this case it wouldn't change the answer.
5 numbers?
Yeah. So this one, and this one, or this one, this one. Really, what difference is the problem? Yeah. So the goal is we're going to hope for something that has a total value of 15 with 3 items. But we want something that, we'll use this as a example, but the code will be general and be able to solve that for us, hopefully almost as easily as we can. And so the question is, how much value can we get within the weight limit? And so we want to know when to take an item. And so we can, the kind of key concept in dynamic programming, which is, in my opinion, not a very good name for it, because dynamic doesn't really mean much in this context, but it's the historical name for it, so we'll leave it, is can we break this into a smaller problem? And so the Fibonacci sequence calculation is actually a good example, because you're just saying, I want to calculate the 50th number, all I need to know is, that's really easy to do if I have the 49th and the 48th. And so anytime you can say, well, I have this kind of hard problem that, if you give me a full list of 4 items, it's not always the easiest to programmatically say, this is the one I take it or leave it. Instead, you want to be like, well, maybe I should take it, maybe I shouldn't. That'd be easy to solve if I knew the answer to some other problem. And so we can walk through a sub-problem that will then code up. And so when would we take any single item we were considering? And so there's actually kind of 4 parts to this, 4 cases that we can talk through. And so the first one is, what do we do if there are no longer any items? Or so what would you do in that case? Would you take any more items if there are none left?
Probably not.
Yeah. So if no items, don't take any and return that there's nothing. So then we have another case of what do we do if the item is too heavy?
And there's nothing.
Pardon?
Oh, any item that you look at.
Yeah, so we're just considering one of these items. Let's say we're just considering this item.
Alright. The items you have, you just describe it.
Yep. So in this context, we'll kind of move through the list left to right in this case, so we can talk about skipping it instead of discarding, but it's equivalent. And then, good fit. There's 2 cases in this. What are the 2 cases that we have that the item could fit in the bag?
So,
It's the best.
So I want to look at the ratio of the weight to value?
No, we want something that, so there are cases of this problem where these aren't fixed numbers, and therefore you can't compute an even
Sorry.
ratio.
what is the value is the number of items with that?
So the value is so these are pairs where that's the weight of value on the left and the value of the item on the right.
Oh, I see.
And so you want to maximize the total amount of value you have
Oh, gotcha.
within some constraint of the weight.
But do you need an equal sign then?
Yes? Thank you.
Also, are you making multiple passes to this list, or are you just going one?
Well, that'll be the algorithm.
So,
We only make one pass through. We only make one pass through in some sense, but it splits many times. And so it doesn't have a good runtime complexity. But in terms of the simplest problem, we're just dealing with this item. We want to compare 2 different cases if the item could fit. What are the 2 cases that we want to think about?
Oh, that you take it or you don't. Oh, that you're going to make a decision tree for taking or leaving every single item just to see which one is best?
Yep. And so that's the decision problem. Calculate the best if you take it. Calculate the best if you skip it. and then return the best. And so in this way, you don't have to think kind of all the way through to the kind of perfect answer at the end of the puzzle. All you have to do is be able to think of one step. Like I can make one step and say, well, you know, if I knew that I took the item, I've reduced kind of the number of possible items I have to consider. And so I'm always working towards a base case so you're always working towards a base case where there are no items left. But it's almost the same type of action as if you just skipped one and you're still working towards a base case where there are no items left. So every time you're doing it, the problem is getting smaller. You're getting closer to a solution. But it's a little too complex to figure out all the interactions for every possible case and every possible weighting of item pairs. So you just kind of say, well, I can program a stupid step, and if I do my stupid step enough times, it's a great answer.
But it still doesn't improve the runtime, right? Like it still checks everything, right? 'Cause you
It
have-
still checks everything, but then it's a question of what do we gain by memoizing the function?
You don't have to go through the permutation.
Correct. And you still have to do most of the
Yeah.
permutations,
You're
but
cutting the decision tree short because you're explicitly asking if it's possible to take something else, though, right? Like it's not
That's still
true
part
to
of the
the,
decision
it's not
tree
true to
cut.
the four
um,
different situations because some of the situations,
Yeah.
the branches are cut because you stop because you just can't take anything else.
No, but even if
in
it
this
were-
case, but it's more, as you're kind of saying, instead of having to calculate every possible combination in every possible order, you can just kind of, what ends up being equivalent is you can do a matrix of saying like, oh, I've taken this item, where are my possible trajectories in this matrix? And you can just make it you only have to compute every value once for an n by n matrix. And so it turns it from n factorial into n squared, if you kind of dedicate the space to it. I happen to like the memoization one rather than kind of hard coding the array or the matrix to kind of make it 2 by 2. Sorry, n by n and walk through. Mostly because you have to think harder about which directions on this matrix are I took the item versus I left the item. So you can store kind of using a 2 by 2 in an n by n matrix to kind of store the same information that the memoization function does. So we'll walk through the memoization problem. Or the memoization version. And so, the first thing we're going to do is going to exactly code that. I'll make sure I don't have any syntax errors and that stuff up above. I think you caught most of them. Code ran, so we're good. And so the first case is the base case, where there are no items left. And the second case is the kind of easy one of it doesn't fit. Then we have our case where it does fit, so we need to compare. So that's relatively simple. You say if items, and so we have to think about how we want to return information. In this case, it's easy just to say that we'll store some variable that has the current value of our bag, and we'll have kind of everything we would put in the bag to get that value. You could calculate one from the other, just do it this way. And so, if we don't have, if it doesn't fit, we would code that up, is we say if our weight allowance is, less than item 0. So I'll use item 0, or a list of items that we're passing in every time.
It's already started.
It doesn't need to be sorted, because we're testing out the whole kind of parameter space of how it could start.
Oh, right, you're just popping it off.
Yeah, because it's a set and order doesn't matter.
Oh, okay.
So we're just kind of popping one off, and then we'll just kind of pass in the tail of the list every time. And that will be clear by just saying that we'll call the same function with items, everything beyond that 0th element, and we'll leave the weight value the same.
So it's assuming that we've already put the item in 2 items.
Yes, at some point we will have to call the function the first time to get everything rolling, where we pass in the entire list of items with the maximum weight that we're allowed to use.
Wait, is items the list of possible items, or is it the list of items in the back?
Items is a list of possible items. The items in the bag is only dealt with in the return variables here. Shit. It's only the values in the return variables that are the alternatives.
But if the last one doesn't fit, and with that code, you're just gonna return 0.
Last item doesn't fit, we just return 0. We'll return whichever one's appropriate.
Okay.
Yeah, sorry, I forgot the return statement. Alternatively, you can cache this value because the first thing we're going to do, in the case where we do have it, is calculate the skip value, which is the value we would have computed otherwise. But then we also need to calculate a take value. So if we decide to take one of these items, and then when we do that, we would we'll start with the skip value. I don't know how to describe this. It'll be sorry. All right. Here we go. We'll be doing the same thing where we're adding up all of the items. Okay, there we go. We're taking on everything beyond the current location, but then we're going to have less weight available. Item 0, 0. Apologies.
Okay.
And so this is indexing it into it, where it's the weight of the items that we're checking here.
And so that would be items.
That's supposed to be 0, 2.
So for the second statement, or the elif statement, it would be items 1, and then 1, or?
So the 1: is passing everything in the list of items beyond our current position. So if this is the 0th position, 1: is everything beyond that in the list.
Oh, okay.
So it's the first position, or position 1 to the end of the list. And so, but as part of this take value, we actually need to modify it, because the list of items that it's going to return does not include the fact that we took the item. And based on the fact of dealing with Python lists, it's easiest just to make a copy of that list. So we're returning up here an empty list, since we just want to add an item to that list. So we start by taking the list, convert it to a list, or convert it to a new list, a copy. And we append the item that we're looking at, so item 0. And then we rename, or we can recreate an updated take value, which will just be the original value we started with, or the original value we returned, so everything we got from beneath it, plus the value of the item that we're taking. And then down here, we're just going to append our longer list. And there are kind of other ways to do this. You can use tuples and all kinds of other things, but this one is reasonably concise and reasonably readable. And so, does this part make sense? It's not that much space in here. I'm sure we know what these are doing.
You lost me there.
Yeah.
That's what I was figuring. So, do we understand what this is doing?
Yeah, I get that one, and I get the take value, but then sort of,
Why are we doing the other steps to modify?
so your take value of see, because basically best is gonna return basically both the weight and the value, and you only want the value. Best is returning a tuple,
Best is returning a tuple, and
And-
there will always be a value
a value, and a
and
weight.
a list of items. And so what we're doing is we're taking that value that it returns, because the value that it
Oh,
returns
okay.
doesn't include the weight subtracted off. And so we need to add in the weight, or we need to add in the value of the item we just took. And that gets added into the value that was returned by this function.
Oh, I see.
And then we need to take the fact that, we have some list that's a running estimate of the number of, or the items that have been added to the bag. With a running description of the items that have been added to the bag. We make a copy of that and append something to it. And then we pass that in as the new value of these are the things in our bag with this total weight.
Oh, I see.
That make sense? But, yeah. So you're gonna do it
Not
now.
your fault.
Yeah. And so then, now that we have these kind of two values, what do we do with them?
Just compare them.
Yep. So if skip value, the actual value portion of it is greater than updated take value.
You don't have zero, right?
Pardon?
You want to return the whole skip value, or?
Yeah, because if we do that, what will come out at the end will be the value and the list of items. And so, in terms of how the problem is phrased, is what is the maximum value you can obtain, that's just the first part, so you don't actually need to maintain the list of items. I just like to do it because I'm always curious what the list of items was. But that's true. There's actually no reason that we have to keep this list other than we're curious about what it was. And we can actually talk about, there's still ways to reconstruct this list after the fact in order and time that you don't even have to store this to begin with. We'll talk about that in a little bit. So I didn't just crash my computer. All right. Let me see. There were a lot of error messages coming up saying that it didn't save, so we might have to use the one I wrote earlier today, which was essentially AF. Yeah, it will eventually open, I hope. I guess not. So I'll try and restart the whole thing. So all that's left to do at this point actually is just to call the best function with the whole list of potential items. And it will actually go all the way through the list for us. It'll try keeping every value, and it'll kind of tossing out every value. And because it's memoized, it won't kind of backtrack and recalculate the same branches over and over again. It'll say this branch has already been traveled down, I don't need to do that again. And then we're just going to go through everything else.
I'm a little confused about why you index items twice.
Because it's a tuple of tuples.
Yeah, why?
Because you need to store both the item weight and the item value. You could also store it as two separate lists, one of all the weights, one of all the values. But because they are items where it's a pair of information,
Okay.
Didn't want to do that. This,
So the first one tells you which item you're looking at, and the second one tells you that you want to look at the value of the item.
Yes, sorry. So the first time you're indexing into it, you're indexing into the which item in the items array.
Yeah.
And the second index is indexing into either the weight or the value of
Yeah.
that particular item.
Okay. Makes a lot more sense.
And now it goes just fine. All right. Okay, so most of that code that I just wrote there didn't copy. So let's go up and verify that the copy I wrote this morning was exactly the same. Yeah, it's doing the same thing, memorize function, same list of items. I have an extra print statement in here, so we'll print off at different points in time what items are remaining to be checked, and what the remaining weight is, what the items are that remain to be checked. So it does the same thing of if there are no items, or if there's no possible weight remaining, just return whatever we have. And so if the item is heavier than the weight remaining, just calculate a skip value and return it. Otherwise, we can calculate a skip value and the same type of use value. That includes the item that we just took and our longer list. We can just return those, and we can then just run function to get the called the best function with the items and the maximum weight. And when we do that, we get some output that looks exactly like we like. And so the first time it ran through, we had the full weight there, and it got to consider all of the items. And there'll also be a case where the first thing we did is we took that first item, and now there's only 6 weight remaining, and now we're only considering the items that came after it. If we scroll down in the list, there's also a case, though, where we have the same 3 items, but we didn't change the weight. And so this is kind of the first part of that kind of decision tree that's splitting all the way down. But one thing you'll notice is that none of these items, or none of these items in this kind of weight remaining print-off repeat themselves. If we go through and comment out this memorize function, what should happen is that all of a sudden some of these should get much longer. It's not long enough to have too many repetitions. Something in here should be repeated twice.
Yeah, the 2 4 ones.
2 4s? But not because there's, no, yeah, it would be repeated out, because there are 2 2 4 items. It should also feel out some branches for taking other things, but the weight remaining would be different. Yeah, so if there's any way of calculating the same, or getting to the same point. So if we take, so the cases that'll be the same if we take these 2 items, we're in here, we're stepping through linearly, so it never happens. If you get things that rearrange the order at all, it can come up. You get more repetitions. But here it didn't make too much of a difference. We can add more items that look similar to kind of create that situation.
Brian?
Yeah.
So the result of the memoization is to speed up the actual execution, but conceptually the function is still has to check all of those values. Every time,
Yes.
Right. It just doesn't actually calculate it every time, but on all subsequent times it needs to check the value.
Yeah, but part of it is, as for the, so it's a little harder to see here, and I apologize for not thinking through it better.
Oh,
I can show it to you.
You can do it, just put the 2 4s next to each other.
Yeah, that's a good point.
And then you can leave one and take the other, or take one and leave the other.
Yeah.
It would be the same point.
There should also be cases that we call it with 1 or 0 items remaining multiple times. That was the other one I was thinking of. But, so here we have a case where we called it 0 items remaining, and with 0 items, with 0 weight and 0 items remaining. And if we memorize the function, we never make this call. But as you were saying, there should be a case where we took and left the first one, or we take and leave the second one. And so we get this call here, where it's 6, 2, 4, 1, 5, 7, or 1, 5. And we should have a case where we listed in a different order, though, I think. Sorry. I think when we get down to 6, where it's 1, 5, 1, 5. There we go. So this gets called twice. But to still solve this problem, we then have to step through, take this part, and take this part. And so like the Fibonacci problem, when you exclude all the things that you would repeat, you get rid of this factorial term. And as the length of the list grows, if we start adding kind of more things back at the end of the list, like we add a bunch of things that we'll never use because they're like a terrible ratio, if we run that, it now goes through, well, we'll have many more items remaining. But now we'll still get that point where we get this set of 6 where we've taken one of the first 2 4s and not the other, but everything else in the list is the same. And so we'll have to repeat that over and over and over and over again, despite the fact it's not really doing us any good to do so. And I can't scroll through the output fast enough to know exactly where it is. And so particularly as the length of the list grows longer, that becomes more and more and more of a problem. If it's back down to something we can look at. So here's mostly the difference in just the number of function calls that you end up making. But this was a length of 4. As the list gets longer, that factorial term dominates more and more. But if you memorize it, you only had to call that once. And the fact that you reached that same combination a second time, you didn't have to calculate the values again. You were just able to say, well, I calculated it once, and that's all I need to do. Does that make sense? And so it's not always the best thing in the world because it still takes a lot of time to calculate that whole kind of probability space. And if order does matter, you have to test a ton of things. But if order doesn't matter, you can kind of make do by doing this memorization thing. In trading space, you get to store a lot more variables, but in exchange, the algorithm ran much faster. Or can run much faster if the list is sufficiently long and you get the worst case time improves. Best case time. So,
Can you explain me quickly why it's in factorial if you don't use?
yeah, so it's so you see these lines where it's 6, 1, and 5, 6, 1, and 5? What would happen if we had a really long list, for each of these cases?
We travel down that list both times.
Both times we would travel down that list, and we'd have to take all of the branches that would happen in that list. And so it's not just one function call that we're limiting. We're lopping off a whole branch of function calls.
Right.
Because this function call, because when we evaluated this one, we would have to evaluate the case where we took this item and the case where we didn't take the item.
Mhm.
And then in that one, we would have to evaluate the case where we took this item and didn't take this item. And so by removing this one line, we're getting rid of 2 times 2 cases. So we're getting rid of 4 function calls, or 5 function calls, just by eliminating this one.
So this wouldn't help if you did,
It helps in the cases where you end up with the same configuration, if that makes sense. And if it's written carefully and set up right, you can increase the likelihood of that happening. I don't think it particularly helps if there are no, off the top of my head, I need to think about it a little while. But I don't think it helps if you don't have anything that hits the same configuration. Because there's nothing
configuration in the sense of weight remaining, or
in the terms of the weights remaining and the items remaining.
all of it?
If you never hit that duplicate case, there's nothing to memorize, there's nothing to say, I've seen this situation before, I know what the answer should be. And it'd be the same thing if you were trying to fill out a table of items I've taken versus items I haven't. Is that if that space doesn't have any values that kind of correspond to the same point, and I can't think of how to do that table off the top of my head, and I didn't think about it enough beforehand. So I can't draw it out on a piece of paper for you guys right now. But most of these problems are typically possible to kind of define a table of kind of transitions. But if you never get to the same point, you can't define a transmission. You still need to test all those points rather than defining, realizing you've hit this transition before. So it definitely does the most towards the end of the list, where you've gotten like most of the items down, or if you have a few items at the beginning that are kind of easy to recognize as the same pair from having very different ways. Yeah, sorry, I did not think enough time of getting a really compelling example for this dynamic programming and memoization really saving a lot of time. But I assure you, it saves time. But it does kind of have this trade-off of you are allocating space to storing all the previously used values, but you get more, a better runtime complexity out of it. And so, let's just think for a bit. Maybe we can transition to the whiteboard if we want. I'd mentioned that it's possible to do this only maintaining or it's possible to reconstruct what items were in the best output. We're going to the bottom. We have the best value is 20 for this set of items, which is what we came up with at the beginning of class. It's possible to reconstruct this list, even if all we knew is that this function had been run successfully and the best value we could go was 20. How would you go about kind of reconstructing that list?
Did you sort the cache?
You don't need to, because that would still take n log n time to do the sorting algorithm at best. Essentially better than that, but it would still take more time to do that. You can do it in linear time, linear in the number of items you have, and not in the size of the cache. And so,
You just, you can exclude pairs of items by starting with sorted large values.
nope, we don't need to exclude anything. And I'll give you a hint that it takes advantage of the fact that we have this memoized best function. It essentially has a lookup table for what the values are, what it's called. And it's related to kind of this step here. We have our skip value and our use value, and we're returning one or the other. So what happens if we call this function on the first item? And we get a value, or we get a weight, or sorry, and we get a value of 20. Does that tell us anything?
Yeah, that's it.
Yeah, that's it. Yeah, you're done.
Okay. What happens if we call the best function on just this part of the list with that first item then removed?
Oh, you basically just keep doing it until you don't get the max value?
When you work backwards, you know what the best value is, and so then you just include the last item in the list, and then you get what the best is, and then
I might have described this poorly and actually planned for red herring on accident. If you step through and including or not including that first item allows you to kind of fulfill this condition. If you can say, you know, I'm going to set aside this value here, I'll pretend I took it, does the rest of the equation still work out? And it's kind of a guess and check method, where you guess, I took this item. You look in your memoized function, is that the same as having actually taken that item? Did we go down this return use value branch, or did we go down the return skip value branch? Because if you call the function where you took the, where you take the value, you say we took this value, but maybe it wasn't in the final solution. If the value you get back is less than the maximum value you could have gotten, then you know you went down a wrong fork. And so you try and take that step. You say, did I go the wrong fork or not? You can do that in a single operation, say, is this what I expect? Well, and you know whether you actually took that item or not. And that allows you to say, did I take this next item? Did I take this next item? And did I take this next item?
you basically just running through the exact same algorithm again, just taking advantage of the fact that all your results are memoized.
Yeah. And so, but you're also doing it,
But once you're running it memoized, it's just linear time.
yes, because it's a constant time lookup
Right.
for the memoized function. You only have to sweep through the list once.
Oh, I see.
And so I like to kind of build the list as I go, but there's actually reason not to, because you can construct a list after the fact very quickly, and it adds space to your kind of memoization storage. You just store more information there. But if all you stored in that memoization table was the kind of value that you have in your bag, that's sufficient to be able to recreate the entire problem space, or the entire solution, I apologize, at the end. Because you can just walk through your algorithm, interrogate your lookup table, and that'll tell you which branch you took at every point in time. And so, yeah. I apologize for not having a good example of the table version of this, the matrix version. I'll tell you it's possible. The cases that make the most sense for me are in the bioinformatics literature, because you can actually go and say, if I had some DNA sequence and I have some other DNA sequence, if all I can do are point mutations and repeats and deletions, how much do I need to do to make one of these look like the other? You can define that with some cost function and define the minimum number of mutations that needed to take place for you to get from one to the other. And you can use that to find the most likely and lowest cost sequence of mutations to align two sequences. So that's a common example where these are stored. So I encourage you to look that up if you're interested. Are there any other questions? All right. Then I think that will conclude the class. Thanks everybody for coming. Thanks everybody for watching.
Yes.